G'day Clansman users, it's Alex here, Victor Kilo 2 Papa Radio Charlie down here in Australia, and lately I've had occasion to do quite a lot of work on power supply, and as we know, these particular power supplies are the Achilles heel of the 320 radio. Whenever they break down, 9 times out of 10 it seems to be the power supply causing the problem. And one of the biggest concerns is the 110 volt supply, because it drives the synthesizer, which drives the variable voltage oscillator, etc., etc. So when the power supply usually fails in the high voltage area, the 110 volt, the radio won't lock, and it just sits there and screams at you. And yeah, start pulling out your hair and saying, how am I going to fix this? And look, over the years, I've really read a lot about problems with a 110 volt board on the 320, and I've repaired a few, and over a period of time, I've come to sort of understand how they work. And I've read varying sort of ideas on how they work, and I've come to my own conclusion here. So what I'm going to do is I'm going to put together a bit of a video on fault finding the 110 volts on your Clansman 320 when it does fail. So let's get on and have a look at the schematic diagram. Okay, here's the 110 volt section schematic diagram for the 320. Let's just have a look at some of the components. We've got a transformer, which we'll get to a bit later, a full bridge rectifier to transform the AC coming from the transformer to DC. We've got a really handy little test point here to make sure that we're actually getting high voltage DC out of our rectifier. And by the way, that should sit at about 120 to 125 volts. And then, of course, we've got the regulator section of the circuit, and down here, we've got this integrated circuit that has basically two functions. The first part of the integrated circuit here is simply a transistor, and it's wired in such a way that it's actually a diode, and that particular diode operates to temperature compensate for ambient temperature changes within the set. So if this particular integrated circuit here was to fail for any reason, you could in fact substitute that with just a simple diode. Simple as that. Over here, this part of the circuit, this little transistor here, it operates a little bit like a Zener diode, and what it's trying to do is put a constant reference voltage of about 5.78 volts right there. So again, if this particular transistor here was to fail within this integrated circuit, it could simply be replaced by a 5.6 volt Zener diode, or perhaps a 5.1 Zener diode with a standard diode in series, and that'll get you set back up and running again quite well. So don't be scared if this particular integrated circuit fails. Just a bit of a talk about some transistors. These four transistors here consist of the regulator part of the circuit, and these two transistors here, when they do fail, they're a little bit hard to get a hold of, but a modern equivalent, a ZTX 857 transistor, is a 300 volt 1 amp transistor, and they work extremely well in these situations. So yeah, you can replace them. I would suggest if you replace one, to replace them both. Simple as that. We've got some capacitors that should very much be changed at any point that you ever open up your power supply to do any work on it at all. And this is capacitor C8 and C6. These are tantalum capacitors, and they cause all sorts of grief with our 320s. They've been in there since probably new, if they are tantalum still. So what I would suggest is they be replaced with modern electrolytic 160 volt capacitors. So I've got a video up on YouTube on how to change those capacitors, so I would simply go and have a look at my video there, and that would lead you down the right track for changing these capacitors. Okay, just going over some of the things that I've learnt over the years on working on this particular part of the circuit. Yep, all of these transistors here can be checked just using a simple in-circuit transistor testing method by just simply using an analog multimeter on the resistance range, and just do the usual checks between base emitter, base collector, and then emitter to collector, to find out if in fact the transistors are okay or not. And look, if they're duds, simply change them. And there's a lot of stuff out there on what transistors you can use, modern equivalents, but I've already mentioned the ZTX 8857 for this particular one here, and this one here. Also, when you're working on your particular power supply and you don't have the 5.78 volts here, in the past I found this little capacitor here can actually leak. So have a good look at that too. That little 47 nanofarad, I think it's a 50 volt little capacitor there. I've had occasion to change those in the past as well. Okay, the diodes are fast switching diodes, and of course, if they fail, they should also be replaced. Simple way to see if they failed or not is to check the output of the transformer here, and if you've got high voltage AC here and you're not getting the correct voltage here of 120 to 125 volts, yeah, I'd be looking very seriously at testing these particular diodes here to make sure that they're in fact doing their rectifying job. Now, most people who have a fault on the 110 start working on the 110. Okay, and this is exactly how I would look at it. If you haven't got the high voltage DC here, then you've got a problem prior to the 110 volt regulator. So you should be looking back this way, right? Then I'd be looking at the AC side to see if I've got high voltage AC before the diode bridge. And if I don't have high voltage AC, then it's safe to assume that the transformer is not working. Okay, and here's where the interesting part of the 110 volt power supply begins, because the transformer that transforms the voltage from 12 volts DC up to 130 volts AC all happens here around this transistor and this transformer. So let's see how it all works. Okay, so before we start, we need 12 volts coming in from the 5A board, and if we don't have 12 volts from the 5A board, then we've got problems on the 5A board, and we need to go and look there. But that's another story. So let's assume that we've got the 12 volts here. Okay, now when we look at this particular circuit, this little integrated circuit down here, it's called power supply unit controller. It's in fact a switch mode power supply controller, and what it does, it offers an alternating square wave coming out of pin 4, and that alternating square wave on and off period is controlled by this little potentiometer here. So as we regulate this, what it does, it regulates the pulse width of the wave coming out of 4 on the controller. So we'll have a look at that waveform later on, and that's the initial start point. You have to have that. If you don't have that, well, you have problems. Go with the integrated circuit. You need to be looking why. Okay, so that pulsating waveform there then switches these transistors, Darlington pair transistors, on and off. And what they do, they provide a pulsing current that comes through the primary of this transformer here. And this pulsing current on the primary side of the transformer, we'll get to this part of it in a minute, but after it comes through the transformer, it pumps up this this capacitor down here, 330 volt capacitor, and this becomes the well, the storage capacitor for your 6 volts. Okay, so virtually it's a bit of a half wave sort of a rectifier pumping up the capacitor to give you a nice smooth 6 volts to run the set. But as the current pulses through this transformer, it causes of course, on the secondary side of this little transformer, a pulsing current as well. And that particular pulsing current there switches this transistor here, which is TR3, on and off. And as that little transistor switches on and off, it provides a pulsating current through our main transformer here, which is the step-up transformer, that steps up the 12 volts DC, which becomes pulsating DC, provides the movement through the transformer for the transformer action. So in order to get the 12 volts pulsating DC to transform up to about 130 volts AC on this side, yeah, we need to have this little transistor pulsing as well. So just a bit of a brief summary here. We need to have a pulsating waveform coming out of pin 4 to generate a pulsating current through this transformer and give us the transformer action from 12 volts up to about 130 volts. Okay, and of course the whole lot's regulated here by this little potentiometer here, and this will regulate, as I said, the space between the on and off of the waveform, which will regulate our 6 volts for our 6 volt power supply. Pretty complicated, but unless this part of the circuit is working, you won't have any high voltage to run your 110. So let's just grab an oscilloscope and have a look at this little test point just here, pin 4, and have a look at the base of this little transistor here and see what I mean by pulsating switch mode power supply. Okay guys, I've got the crow going. I'm just going to go on to my test point here coming out of pin 4 of the integrated circuit. Well, let's have a look. So there's our pulsating waveform. It's pulsating on both sides of the baseline, up and down, and on the positive part of the cycle, that's the positive part that's switching on the transistors to oscillate and get our circuit to operate. So in order to make sure that your regulator is actually working, you've got to have that. And notice it's about 43 kilohertz, and by the way, the amplitude there is from peak to peak is about 1 volt. 1 volt. So good place to start, and it helps having an oscilloscope when working on these power supplies. So next, let's have a look at the base on the transistor. Okay. Okay, there's the base on the transistor, TR3. Whoops, just rip it off. Another look. Yep, there it is again. The base on the transistor. So it's switching on and off, and that's providing the oscillation for our main transformer to step up our voltage. Okay, so there you go. That's how it all operates. So a little bit of point of interest. When we look at this little transistor, this particular one here, TR3, it's a BC107. Now that's a pretty common transistor. Now, one thing that I've learned is that this particular BC107, it's actually operating at pretty well its limit. And sometimes we find that over here, our voltage might be a little bit lower than the 121 volts. We really need that sort of voltage, headroom voltage, between around about 121, where it regulates down to 110. So we need that sort of headspace. So when we hit the trestle, any drag on the 110 volt power supply, there's enough headspace here to accommodate that voltage dip. So you really need that headspace. And if you don't have that headspace, the problem could be that this particular transistor here, its gain has sort of deteriorated perhaps. So in replacing the 107, I've heard it said that people should test a set of transistors and possibly grab one that's got the highest gain to put into that spot, which would probably be a good move. But one of the things that I've done, I've learnt that this transistor here can be replaced with a BC109C, which has a higher gain than the 107, and generally that will bump up your voltage here to about 130 volts. So if you have occasion to change that transistor, I suggest using a BC109C. Okay guys, well I hope all of that helps people in fault finding their high voltage problems on their Clansman 320 power supplies. Good luck to you all. This is Victor Kilo 2 Papa Radio Charlie Alex saying until next time, good Clansman operation guys.